Hey everyone, Mr. Halk here. In today's video, we're going to be looking at how we can take the equation for a trigonometric function and graph it on the xy coordinate plane. Alright, let's go ahead and get started. Just as a reminder, in the previous video, we looked at this big equation right here that kind of details out the transformations of trig functions that we've looked at. And in the previous video, we also looked at how, given a graph, how we can derive the equation of the transformed trig function. We understand that A represents the amplitude, or A helps find the amplitude when we're talking about sine and cosine functions. We know the tangent doesn't necessarily have an amplitude, so to speak, but we do know that the A term, even in a tangent function, is kind of representing how much the tangent gets stretched or compressed vertically. We understand that the B term is related to the period, and we know that the period for sine and cosine is 2 pi divided by B, and that for tangent, the period is pi divided by b. We know that C represents the phase shift, or the horizontal shift, and that's where we take our trig function graph and we shift the graph left or right. And we know that D represents the vertical shift, where we take our trig function graph and we shift it up or down. Okay, so let's go ahead and get into this. Let's get some examples under our belt here. In the first example, we had the parent function y equals cosine of x, and the parent function has already been graphed for you. So on the very same graph, we want to sketch the graph of y equals negative cosine of x. Oh, go back. Yep, y equals negative cosine of x. So looking at y equals negative cosine of x, there's really only one change that's happening, and it's this negative sign is creating a reflection across the x-axis. So this one's going to be pretty easy. What we're going to have to do is take our points from the parent function of cosine and reflect those points across the x-axis. So here I have 0, 1. I'm going to reflect it to 0, negative 1. Pi over 2 comma 0 is going to stay where it is because you can't reflect a point that's on the x-axis across the x-axis. We have pi negative 1 is going to get reflected to pi positive 1. 3 pi over 2, 0 is going to stay where it is. And then 2 pi comma 1 is going to reflect to 2 pi negative 1. And then we want to make sure that we go ahead and connect our points with a smooth curve. Remember, these are not straight lines. There are no points here, like no sharp points. We're going to try to make it as smooth a curve as possible. And admittedly, I'm not the greatest at this, but there we go. That's not too bad, not too shabby. And I'm just going to highlight these points in black to kind of make them stand out a little bit more. Okay. So there is our final graph in blue for y equals negative cosine of x. Pretty easy first example. The next example in our notes is we're given the parent function for sine of x, and again, it's already graphed here. And we want to go ahead and graph y equals 2 sine of x minus pi over 4. So notice that there are two transformations that are happening. This 2 is telling us that the new amplitude is going to be 2. And this minus pi over 4 is telling us that we have a phase shift where we are moving the graph of sine right by pi over 4. So here's how I'm going to choose to approach this problem. First off, I'm going to go ahead and take all the points on the original graph of sine, and I'm going to increase their amplitude by stretching them up by a factor of 2. So let's start putting some new points on here. 0, 0. That's going to stay where it is. Pi over 2, 1. If we increase the amplitude, it's going to go to pi over 2, comma 2. Pi is going to stay where it is. 3 pi over 2, negative 1 is going to go to 3 pi over 2, negative 2. And then 2 pi would stay where it is. So that kind of takes care of the amplitude shifting, or the amplitude increasing to 2. Now let's look at the phase shift of moving right by pi over 4. So each of these points I'm going to take and I'm going to shift over to the right pi over 4. And I'm going to put these points here in purple. So this point in blue is going to get moved right by pi over 4. This point in blue is going to get moved right by pi over 4. This point in blue is going to get moved right by pi over 4. This point in blue is going to get moved right by pi over 4 as well. And we don't have enough space to move 2 pi to the right by pi over 4, but we know it would be moved over there. And then now let's go ahead and take these points and let's connect them with a smooth curve. I'm going to graph this in purple. and we would get something like that. Okay, and once again, I'm going to use black to kind of make those key points stand out. What I would really be looking for on a test or a quiz, especially for problems that have short answers, is I would be looking for certain points placed in the correct spots. Okay, and just to kind of make the graph look a little neater, I'm going to go ahead and erase any extraneous points that we don't really need. Those were kind of guiding points to kind of get us to where we needed to be. Now, one of the things that's going to be incredibly beneficial to us is to check our answers with some kind of graphing tool, primarily Desmos. So I've done a little bit of preparation work here for us, and I have this already graphed in our Desmos graphing calculator. So we're trying to graph 2 sine of x minus pi over 4. Let's go ahead and activate that graph, 2 sine x minus pi over 4. And let's just double check on some of our key points here. So on our graph, notice we want pi over 4, 0 as a point. We can see that right there. Well, we notice pi over 4 comma 0 right there. Also notice that we have 3 pi over 4 comma 2 as one of our key points in the final graph. Well, there's 3 pi over 4 comma 2. We want 5 pi over 4, 0. Well, there's 5 pi over 4, 0. And then we want 7 pi over 4, negative 2. Here's 7 pi over 4, negative 2. So it does appear that our graph is accurate. So everything's good to go so far. Let's move on to our next one. All right. The next one, we had the parent function of tangent of x has already been graphed below. And on the same graph, we want to sketch tangent of 2x plus 1. Now, tangent is always an interesting graph. This is one of those that can be a little tricky until you've got a few examples under you. So let's think about what's really changing here. And I think one of the best ways to look at it is to think about what's happening with the parent function. So when we think about the parent function of tangent, we know the period is every pi. Pi is the period for the parent function of tangent. And in the parent function of tangent, we would have these asymptotes at pi over 2, and then every pi after that. So pi over 2, we'd have an asymptote. 3 pi over 2, we'd have an asymptote. Then we'd have an asymptote at 5 pi over 2, and so on. But notice some of the stuff that's happening here. Number one, we have a period that is shifting from pi to pi over 2. So we're getting a period that is basically twice as small. Okay, so instead of, and this is where it's going to be a little tricky to think about, but instead of the asymptotes falling at pi over 2 and repeating themselves every pi, now what's going to happen is that the asymptotes are actually going to happen at pi over 4, and they're going to repeat themselves every pi over 2. So let's go ahead and draw in our new asymptotes, and I'm going to draw them in blue, okay? So we're going to have an asymptote right here at pi over 4. We're going to have an asymptote at 3 pi over 4. We're going to asymptote at 5 pi over 4. 7 pi over 4. So on and so forth. Okay. Now, if we think about the parent function of tangent, notice that we have a point here at 0, 0. Since we didn't have any horizontal or vertical shifts, no phase shift or vertical shift, we're still going to have a point at 0, 0, but also notice that our points are going to be shifted up 1 vertically. So we would go from having a point at 0, 0 to having a point at 0, 1. So let's go ahead and put a point there at 0, 1. Okay? Similar here, we would have had a point at pi over 2, 0, but now that we have this vertical shift up 1, we're going to have a point at pi over 2, comma 1. Same thing here at pi. We're going to have a point at pi, comma 1, 3 pi over 2, comma 1, 2 pi, comma 1, and so on as the graph would expand to the right. Also, we would end up having points here, right 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 here. So just kind of thinking about the way that tangent normally works, for the parent function, we would have those kind of in-between points at 1, and since we're not really changing any, we're not multiplying any of these terms by a factor of anything, those little in-between points are still going to work. They've just been shifted up once. And since our period is now pi over 2 rather than pi, we're just getting more cycles in that same time frame. So now let's go ahead and connect all these points here. So we would have curves that appear like this. Okay, and our final answer is the one here in blue. I know that the parent function here in red is kind of acting as kind of a distracting feature on this graph, but it's good to see what the parent function is looking like as we go to graph the this transformed function. Now, once again, let's go ahead and confirm with Desmos. So I've gone ahead and graphed this function in Desmos. Let's hide this one we were just looking at. So let's look at tangent of 2x plus 1. And let's look at some of these key features here to make sure that our points are matching up. So we want to point at 0, 1. Well, there's our point at 0, 1. We want to point at pi over 2, 1. So pi over 2, 1 would be about right there. It's not highlighting it on the graph, but it's about right there. We want to point at pi, 1. So pi, 1 would be right there-ish. Then we want 3 pi over 2, 1. We can see 3 pi over 2, 1 is right there on our graph. So our points are correct, and they're in the right spots. Okay, so that's looking good. Again, tangent is one of those that's kind of weird. You start to notice some of the patterns the more that you graph them. You just need to get some examples under your belt. All right. So for the next 3 examples, we're going to graph, but without having the parent function already graphed for us. Now, it wouldn't be a bad idea to go ahead and kind of sketch the parent function lightly, just so that you have something to kind of shift around and morph. But let's go ahead and see how this is going to go. So in our first example, we're going to graph y equals -2 cosine of 3x. And let's take note of some of the stuff that's happening here. Number 1, we have this minus sign out front, which means that we're going to be reflecting our cosine graph across the x-axis. Then we have this 2 in front of the cosine, which tells us that the amplitude is now going to be 2. And we have a 3 being multiplied to the x in the parentheses, which tells us that our period is going to be 2 pi over 3. And we know that because period for cosine and sine is 2 pi over b, and since the b term is 3, we get 2 pi over 3. Okay? So here's essentially what that means. That's telling us that, typically cosine will go through one complete cycle every 2 pi, okay? What this is telling us is that cosine is going to go through a complete cycle by the time it hits 2 pi over 3. So we want to go ahead and fit in as many cycles as we can, and since the b term is 3, what this is telling us is that we're going to get 3 full cycles in the same span of space that the parent function of cosine would have only gotten 1 cycle in, okay? But let's go ahead and, lightly plot some points here. So in black, I'm going to plot the parent function of cosine. So we know that cosine typically starts at 0, 1. At pi over 2, the parent function of cosine will be at 0. At pi, we'd be at -1. At 3 pi over 2, we'd be back at 0. And then at 2 pi, we'd be back up here at +1. Now, I'm going to use different colors to represent different transformations here. So let's go ahead and reflect these points across the x-axis and change their amplitude. So, the midline here, the midline is still y equals 0 or the x-axis. So if we shifted this point across the x-axis, this would shift down to 0, -1, but then we want to make the amplitude 2, so it would actually go down to right there. So I'm going to do that in blue. Okay. Next, what would end up happening, if we looked at pi over 2, well, shifting it across the x-axis and changing the amplitude to 2 wouldn't really affect it here because it's already on the midline. If we looked at pi, -1, if we reflected it across the x-axis, it would come right here. Then we change its amplitude to 2, so it would actually be mapped right there. 3 pi over 2 would stay where it is. It's already on the midline. Amplitude and, reflecting is not going to change it. And then lastly, if we look at 2 pi here, reflected across the x-axis, we get right there. Changes amplitude, we'll get right down there. Okay, so we're kind of seeing this, this little shape right here. Okay, the issue though is that still has a period of 2 pi. Notice it's going through that cycle. It's going through a full cycle with a period of 2 pi. We need the period to be 2 pi over 3. So what that's telling us is that by the time we get to 2 pi over 3, I actually want one full cycle to have already been completed. So I'm going to kind of take this curve and I'm going to kind of smush it in on itself so that it completes the cycle by the time we hit 2 pi over 3. So I'm going to keep my same starting point. I'm going to start at 0, -2. But in order to get the cycle to be complete by 2 pi over 3, watch what I'm going to do here. I'm going to do these points in purple. So at pi over 6, we're going to be right here. At pi over 3, we're going to be here. At pi over 2, we're going to be there. And at 2 pi over 3, we're completing the cycle, and now we're right there. So notice that now we have the amplitude of 2. Okay, we can see that, amplitude of 2. We have the reflection across the x-axis, and now we have the period of 2 pi over 3. So let's get rid of some of these extra points that we don't need anymore, and let's complete what the graph would look like. So again, we're going to go ahead and take this cycle and repeat it as many times as we can. So let's go ahead and put in, we can just kind of see where the other points are going to be. We'll have a point here at 5 pi over 6. We'll have this point at pi. 7 pi over 6, there. We're just kind of following a pattern at this point. And then let's go ahead and try to connect this with as smooth of a curve as we can. And I'm kind of bad at this, so we'll see how this goes. Again, notice I'm trying to make a curve. I'm not trying to make straight lines or points. Even though I kind of missed a little bit on some of them there. Again, what I would be looking for if I was to grade a short answer question is I'd be looking for accurate points, not so much, is your curve perfectly rounded and all that kind of stuff. I'd be looking for those kind of points that I have there in black. Now, once again, let's go ahead and double check with Desmos just to make sure that we have accurate points. All right, so let's hide the function we were just working with. Let's go ahead and reveal -2 cosine of 3x. And if you notice though, notice on our graph here, our step is by pi over 6. So let's go ahead and change the step to be, instead of pi over 4, let's change it to pi over 6. And let's see if we're getting some of these points that we really want. Okay, so notice we want to make sure that we have 0, -2. All right, that point's right there. We want to have pi over 6, 0. Pi over 6, 0. We want to make sure that we have pi over 3, 2. Well, there's pi over 3, 2. Check. Pi over 2, 0. Pi over 2, 0 is right there. 2 pi over 3, -2. There we are right there. And the cycle would just end up repeating itself after that. So our graph is good. Again, Desmos incredibly powerful for checking your answers in this part of pre-calculus when we talk about graphing and trig transformations. Desmos is an incredible tool. So let's keep moving on. All right, in our next example, we want to graph y equals 2 sine of x minus pi over 2 minus 1. And here are the three trig transformations that I'm noticing. I'm noticing that our amplitude is going to turn into 2. I'm noticing we're going to have a phase shift of right by pi over 2. And I'm noticing we're going to have a vertical shift down by 1. So, let's think about some of the things that we're going to do here. Number one, once again, I'm going to kind of lightly sketch the parent function of sine. So I know that sine not typically, but the parent function of sine does start at the origin 0, 0. We know that for the parent function of sine, by the time we hit pi over 2, we're at +1. By the time we hit pi, we're back at 0. 3 pi over 2, we're at -1. And 2 pi, We've done our full rotation. We're back at 0. Okay. And this time, notice that, with this transformation, because we have a vertical shift to -1, our new midline is going to be here at -1. So let's go ahead and very lightly put in a new midline at -1. I say lightly, and then that's about the darkest line I can have there. Okay, so there's my new midline. So what we're going to do is we're going to take these points with an amplitude of 2, and we're going to kind of move them about that midline. So let's see, we would move 0, 0. We'll do some new colors here. 0, 0 would be right there. It's on the midline, so having an amplitude of 2 won't affect it. Then if we took this point right here at pi/2, 1, and we wanted an amplitude of 2 with respect to, oh wait, we gotta do the phase shift as well. Hold on. Let's see here. So let's just worry about, here, let's do this. Let's not worry about the midline for the time being. Let's worry about doing the amplitude of 2 first. So if I were to increase the amplitude by 2, I'm going to do my new points here in blue. So this would move up here, this would stay here, this would move down to -2, this would stay right there. And I'm going to go ahead and erase these black points because now we're dealing with the blue points. So that takes care of the amplitude of 2. Now looking at the phase shift right by pi/2 and the vertical shift down by 1, all we're going to do is we're going to take each of these points and we're going to move them right by pi/2 and then down 1. So if I took, and I'll do these points in purple, if I took this point and I moved it right pi/2 and then down 1, we would have a new point right there at pi/2, -1. If I took this point here in blue and went right by pi/2, then down 1, I would have a new point in purple right there. And let's do that with all of our points. So here we go, move this right pi/2, down 1. Move this guy right pi/2, down 1. And we could also see, just, by recognizing the pattern here, we would also end up having another point right there. So let's go ahead and get rid of those blue points. We now have the points in purple, going to represent our final answer here. And again, we're going to try to make a nice curve, no straight lines, no sharp points, to the best of our ability. Okay, and we'll put in these points here in black just to kind of make them stick out. Remember, those points are what's important there. So again, let's just kind of verify all the points here. Do we have an amplitude of 2? Well, let's look at our midline. From midline to maximum, amplitude of 2. From the midline to a minimum value, amplitude of 2. That checks out. Do we have a phase shift of right by pi/2? Yeah, because if we would have started at 0, 0, phase shift right pi/2, and then also a vertical shift down would bring us to this point right here. So those conditions are met as well. But once again, it's a good idea to go ahead and check in Desmos just to make sure. So let's check this in Desmos. Let's go ahead and hide this graph. Let's go ahead and graph now 2 sine of x minus pi/2 minus 1. And let's look for these points. Let's go ahead and change the step again to pi/4. So erase that, step to pi/4. And let's see what we can, if we can see these matching points. So according to our graph, we want a point at 0, -3. Well, we have that. That's right here. Excellent. We want a point at pi/2. And you can tell that's a -1. So pi/2, -1. We have that. We want a point at pi+1. We have that right there. We want a point at 3 pi/2, -1. You can tell that's about right there. There's 3 pi/2, -1. And then we want a point at 2 pi, comma, -3. That's right there. Okay, so our graph is accurate. We've met all our conditions. We're good to go. In our last graph, so now we want to graph y equals 3 tangent of 2x. And a couple things that we notice here. Number one, we have this 3. Now normally with sine and cosine, that would tell us about the amplitude. Tangent, again, doesn't have an amplitude, so to speak. But the 3 is still kind of taking the tangent graph and stretching it up by a factor of 3. Okay, so I'm going to call it a factor of 3. It's not really an amplitude. I'll just call it a factor here. And then we have this 2 on the inside being multiplied to x. And remember that this is affecting the period. So normally the period of tangent would be pi. Well, since we have this 2 here, the period of the graph that we want to have is going to be pi over 2. Okay, because we're doing, tangent, the period for tangent is pi divided by b, and we know that our b term is 2, so we're going to have pi divided by 2 for our period here. So that's going to tell us a couple of things. It tells us that, if we think about the parent function of tangent, we would have had asymptotes at pi over 2, at 3 pi over 2, 5 pi over 2, so on and so forth. Okay, so let me kind of get those there. So now, because our period is now pi over 2 instead of pi, we have a much smaller, we have basically a twice as small period. So instead of having, an asymptote at pi over 2, 3 pi over 2, 5 pi over 2, now we're going to have an asymptote at pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and so on. So let's go ahead and put in some asymptotes there. So again, let's put one at pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Okay. Now, if we think about the parent function of tangent, we know that we go through the origin. And since we don't have any vertical or horizontal shifts here, no vertical shifts or any phase shifts, we know that our transform graph is still going to go through the origin. So let's go ahead and put a point right there at the origin. Now we got to figure out, how are we going to handle this multiplied factor of 3? Well, in your parent function graph of tangent, halfway between the origin and that first asymptote, we would have had a point at positive 1. Now, halfway between the origin and this first asymptote, instead of having a point at positive 1, we're going to have a point at positive 3. So let's go ahead and put a point halfway between 0 and pi over 4. That would technically be pi over 8. And we would have a point up there at positive 3. That's kind of showing that we've taken that graph of tangent and stretched it by a factor of 3. Okay? And same deal here. We're going to have a point here in the middle, sitting on the x-axis between our two asymptotes. Same deal here. Point in the middle, sitting between the two asymptotes. Here as well. Here as well. And we're going to continue to kind of follow the same pattern. We'd have a point here at positive 3. We'd also have a point down here at negative 3. Point right there at positive 3. Point down here at negative 3. And these are just the kind of things the kind of patterns you'll start noticing the more and more that you graph these tangent functions. And now let's go ahead and make our little tangent curves. So we'd have something like that. And again, I'm not looking for super accurate curves. I want to see them rounded. I want to see some of the important points. And that's really what matters to me. Okay. And I'm going to go ahead and highlight some of these points just to make them stand out a little bit more. So if I were to think about some of the important points here that I would be looking for, if I were to grade a short answer kind of question, I would be looking for these points and these points. Okay. Now, once again, one more time, let's go double check with Desmos. Always good to, especially with tangent graphs, since they're so different from sine and cosine graphs. Let's make sure that our tangent graph is looking the way it should look. So we're already going by, our step is already pi over 4, so that's fine. Let's kind of zoom in a little bit. We can see that we want a point at 0, 0. Well, check, we've got that. We want to point at pi over 2, 0. We've got that. We want to point at pi 0. Well, we've got that. 3 pi over 2, 0. We've got that. So those points are looking fine. Moving over to that point that we have located at 3. So notice that, if I zoom in here on pi over 4, halfway between 0 and pi over 4, because remember, pi over 4 is where our asymptote is. Halfway between 0 and pi over 4 is pi over 8. And I want pi over 8 here to be meeting up at 3, which is exactly what it does. Here's where pi over 8 would be, and it's meeting up at 3. And we can just see that pattern repeated as the tangent graph moves to the right.